You know how sometimes a really groundbreaking idea can just sort of float past?
Mm,
Like you see it, but it doesn't quite click, or maybe not enough people are talking about it.
yeah.
Like finding an amazing seashell, but just walking by.
Yeah, I know what you mean.
Well, today we're going to pick up one of those shells. It's this concept of one-shot signatures. I saw Justin Drake mention it in that Pro-J Crypto talk.
Ah, right. Yeah, that was a good talk.
And it just struck me as this potentially huge idea in cryptography that feels, I don't know, kind of overlooked.
I think that's fair to say. It hasn't hit the mainstream quite yet. So you brought us that talk, and also a research paper, right? One-shot signatures and applications.
Exactly. The paper is called One-Shot Signatures and Applications to Hybrid Quantum Classical Authentication. So the plan today is to really, dive into both.
Okay.
Try and understand what these things are, how they work, and explore some of the, frankly, kind of surprising things they might enable.
Sounds good. It's definitely fertile ground. Because the core idea, it's pretty wild.
It really is. I mean,
Yeah.
a private key, the thing you use to sign something digitally,
Yeah.
that can only sign one message.
Yeah.
And then, poof.
Poof is a good word for it. Self-destructs.
Yeah.
Gone.
And the kicker is, this isn't just some clever software trick. It relies on, well, quantum mechanics.
That's the crucial part. It's fundamentally different from anything we can do with just classical computers and classical crypto.
Right. And you mentioned when you shared these sources, you were thinking about, like, the future of blockchain security,
Yeah.
where quantum computing fits in.
Yeah, exactly. How does this, seemingly sci-fi concept maybe solve some real-world problems we have right now?
Perfect. So that's our mission for this deep dive.
Mm.
We'll look at the basics, the quantum principles behind it.
Okay.
Then we'll get into the blockchain stuff. Justin Drake talks about finality, validators, all that.
Mm-hmm.
And then broaden out to the other crypto applications from the research paper, things like equivocal hashes and signature delegation.
Yeah, there's a lot packed in there. Should be interesting.
Okay, so let's start at the beginning, the fundamentals. How do we even start thinking about this?
Well, like you said, the absolute core is that poof moment Justin Drake described. The private key is used once, and it's destroyed in the process.
Okay.
And it's really, really important to get this distinction. And this isn't like old school one-time signatures where, signing twice leaks your key, makes you vulnerable.
Right, where it's dangerous but not impossible.
Exactly. Here, it's physically impossible to sign a second time with the same key. The key itself ceases to exist in its usable form.
Because it's quantum.
Precisely. The private key is a quantum object. It exists in a superposition of states. Justin used purple in his diagrams for the quantum stuff.
Right, purple quantum, blue classical.
Yeah. But the message you sign and the signature that gets produced, those are just normal classical bits and bytes, blue stuff.
Okay, quantum key, classical message, and signature.
Yes.
So how does the quantum part make it go poof? What are the specific quantum rules at play?
There are two big ones. First, the destructivity of measurement. See, when you have a quantum system in superposition, kind of being multiple things at once the moment you measure it, you force it into one single classical state.
Right, it collapses.
It collapses. And that act of measurement inherently basically destroys the original superposition state. So using the quantum key to sign is a form of measurement.
Ah, so the act of signing is the measurement that destroys the key. Like popping a soap bubble, once you touch it, it's gone.
That's a great analogy. Exactly. And the second principle is the no cloning theorem.
Right, can't copy quantum states.
You got it. It's a fundamental law. You cannot make an identical copy of an unknown quantum state, like our private key superposition. If you could just copy the key before using it.
Then the whole one-shot idea wouldn't work. You just use a copy.
Exactly. So no backups possible, and using it destroys it. That's the magic combination.
Okay, that makes sense. No cloning, destructive measurement. Got it. So let's pivot to blockchains, like Justin Drake discussed. How does this single-use key idea work there? Validators need to sign stuff constantly, right?
Yeah, that's the immediate practical hurdle. One key, one signature, not great for signing thousands of attestations on Ethereum, for example.
So what's the solution?
The idea is signature chains. Think of it like a sequence. Your first one-shot signature doesn't just sign a message, it also authorizes the creation and use of the next one-shot key in the chain.
Ah, okay, so signature number 1 passes the baton to signature number 2's key, number 2 passes it to number 3, and so on.
Exactly, like a relay race, passing the signing capability down the line of single-use keys.
Clever. And what benefits does this bring? He mentioned perfect finality. That sounds, well, perfect.
It's a very strong claim, yeah. Perfect finality here means a blockchain using these could, like, by its very nature, prevent two different conflicting histories from ever both being considered final.
No more finality conflicts, no chain splits based on that.
That's the potential. Today, network partitions or attacks can sometimes lead to situations where different groups think different blocks are final. Resolving that can be messy. One-shot signatures, because they physically prevent a validator from signing two conflicting things that could lead to such a split. Well, they could just eliminate that whole class of problems.
Wow, okay, that would be a massive improvement. And he also said the threshold for agreeing on finality could drop from 23 down to just 50%.
Right. Think about why we need that two-thirds supermajority now. It's a buffer, right? To tolerate some malicious or offline validators and still be sure you won't get conflicting finalized chains.
Makes sense.
But if each validator's vote is cryptographically guaranteed to be unique and final because of the one-shot nature, they literally cannot double vote on conflicting things, then you don't need as large a buffer. A simple majority, 50%, becomes enough to guarantee you won't have those finality conflicts.
So it's more efficient because the underlying guarantee is stronger.
Exactly. It's called deterministic safety. The system determines safety at the cryptographic level rather than just probabilistically.
Deterministic safety. Okay.
Yeah.
And what about this weak subjectivity thing he mentioned? Ultra weak subjectivity.
Yeah, so weak subjectivity today means if you're new to the network or you've been offline a long time, you need to get a recent trusted checkpoint to know you're on the right chain.
Okay.
With the kind of perfect finality, one-shot signatures promise, that need for a recent trusted checkpoint basically disappears. You get what he called ultra-weak subjectivity.
And what does that mean practically?
Well, one big consequence is that validators could potentially join or leave the staking set almost instantly. No more long entry or exit queues like Ethereum has now, no churn limits.
Whoa, instant validator joining and leaving. That changes the dynamics completely.
It really does. Much more fluid, much less friction for validator.
Okay. He also mentioned slashing risk getting penalized in liquid staking. How do one-shot signatures fit in there?
Well, the biggest slashing risk, arguably, is equivocation signing two conflicting blocks or attestations.
Right, double voting.
Since one-shot signatures make that impossible at the crypto level, that specific slashing risk just vanishes. Poof, exactly. And that helps liquid staking tokens, too. One worry with things like Lido is the exit queue. If tons of validators want to exit, it takes time. And during that time, the underlying stick is still vulnerable to slashing, which could depeg the liquid token.
Oh, I see.
With faster exits and no risk of equivocation slashing, that whole exit queue leak time risk gets massively reduced, makes liquid staking inherently safer.
Less risk all around. Interesting. And he briefly mentioned simplifying discussions around Leo reward distribution and delegation.
Yeah, I think the idea there is that a lot of the complexity in designing staking rewards and delegation mechanisms comes from trying to account for and punish potential misbehavior like equivocation.
Right, building defenses.
If the underlying signature scheme just removes that possibility, the whole design space might simplify. You don't need such complex guardrails if the road itself prevents certain kinds of accidents,
That makes sense. Cleaner systems because the foundation is stronger. What about reeking? Agreeing to new slashing rules.
Right. Reeking lets the network upgrade its slashing rules over time. But if one-shot signatures already provide that deterministic safety against double voting...
Then you wouldn't need to reek just for that purpose.
Exactly. It potentially makes that specific motivation for reeking obsolete. The cryptum handles it.
Gotcha. And the last blockchain point was proof of location becoming more tractable.
How? Proof of location is tricky. You want to prove you're somewhere at a certain time without someone just replaying your proof later.
Yeah.
The ephemeral, single-use nature of one-shot keys, maybe chained together based on location or time, could offer new ways to build more robust proof-of-location systems that are harder to spoof or replay. It's more speculative, maybe, but the potential's there.
Okay, so definitely some potentially huge implications for blockchains. Let's shift gears now to the research paper. It goes deeper into the crypto itself, right? How these things might actually be built.
Yeah, the paper gets into the nitty-gritty. They start by simplifying things. How would you sign just a single bit?
Okay, boil it down.
And a key concept, which Justin also mentioned, is using a classical hash function, but creating a quantum superposition of all its possible input-output pair.
Wait, all possible inputs and outputs of something like SHA-256, all existing at once in a quantum state?
Sort of, yeah, conceptually. In quantum computing, creating that kind of uniform superposition over inputs is relatively straightforward using standard tools like Hadamard gates.
Okay, so you have this massive quantum state mapping all inputs to outputs. Then what?
Then you measure or observe the output part of the state. That active measurement forces it to collapse into one specific output hash value.
And that becomes the public key.
Exactly. Your public key is just that classical hash output. But what's left, quantumly speaking, is the superposition of only the inputs, the pre-images that could have produced that specific output hash.
So the private key is the quantum cloud of all possible inputs for that one public key output.
Precisely. For a normal hash like SHA-256, there'd be, a mind-boggling number of pre-images in that cloud.
Okay, clever.
Yeah.
But how do you use that cloud, that quantum private key, to sign even just one bit?
This is where it gets really neat. You need a special kind of hash function, one the paper calls equivocal.
Equivocal?
Yeah, it means the hash function has this extra property where if you hold the quantum private key, that superposition of pre-images, you can efficiently find a pre-image within that superposition that also satisfies some other specific condition, like, say, a pre-image whose first bit is 0 or 1 corresponding to the message bit you want to sign.
So the quantum key lets you search through that giant cloud of inputs for one with a specific property related to your message.
Exactly. It's like having a magic index for that cloud, but an index you can only use once. And the paper mentions this important result from 2022,
Yeah.
showing that building these one-shot signatures is actually mathematically equivalent to building these equivocal hash functions.
Wow, okay, so the problem shifts. Find an equivocal hash, and you've basically found a way to do one-shot signatures.
That's the insight. It really focuses the research effort.
Okay, so use the quantum key, find the special pre-image that matches your message bit. What's the actual signature that? Is it quantum 2?
No, and this is really important for practicality. The signature itself is just that classical pre-image you found, a regular string of bits.
Okay.
And verifying the signature, also totally classical. Anyone with the public key, the hash output, and the signature, the pre-image, can just run the hash function on the signature.
And check if it matches the public key, and maybe check if it satisfies that extra condition related to the message.
Exactly. Standard classical verification. No quantum computer needed on the verifier side.
That's huge. Makes adoption way more feasible.
Mm-mm.
Okay, but Justin raised the issue of quantum states being fragile decoherence, right? Does the paper address that?
It does. Decoherence is a real challenge. The quantum state basically leaking information to the environment and losing its quantumness.
Yeah, the key could just fizzle out before you use it.
Right. The paper implicitly supports the idea Justin mentioned for chains, using dummy signing rounds.
Refreshing the key.
Sort of. In a signature chain, you can periodically use the current key to sign a no-op message, essentially just authorizing the same key again or a freshly prepared identical key. This refreshes the quantum state and pushes back against decoherence.
Like giving the quantum key a little checkup and refresh regularly.
Yeah, if you know roughly how fast decoherence happens for your hardware, you schedule these dummy rounds often enough to keep the key alive until the next real signature.
Okay. And Justin also mentioned this idea. If we have just one working one-shot signature scheme,
Mm-hmm.
we could potentially use indistinguishability obfuscation, I/O, to turn any signature scheme into a one-shot one.
Yeah, that's a fascinating theoretical link. I/O is like super advanced code scrambling. You hide how a program works internally, but it still does the same thing.
Right.
If you had strong I/O, which is still a big if, practically,
Okay, big caveat.
and one existing one-shot signature scheme, you might be able to build a kind of compiler. Feed it a regular signature scheme, and it spits out an obfuscated version that behaves like a one-shot signature. It's mind-bending stuff, really connects different areas of advanced crypto.
Very cool, even if theoretical for now. Okay, let's dig more into the specific contributions of the research paper itself. Beyond the basics, what other insights or applications do they focus on?
Well, they provide the rigorous crypto definition, really nailing down mathematically why it's impossible classically, and relies on no cloning.
Right.
And a key example they use right at the start is signature delegation.
Yeah. Alice wants Bob to sign once for her.
Exactly. Alice wants Bob to sign just one message on her behalf, but she only wants to use classical communication, emails, texts, whatever.
And she can't just give Bob her regular private key because he could copy it and sign forever.
Precisely the problem. Classically, any info that lets Bob sign once probably lets him sign multiple times. But the paper shows how Alice can use classical messages to essentially give Bob a quantum signature token.
A quantum token sent via classical means.
Well, the information defining the token is sent classically, but the token itself, which Bob might need a quantum computer to use, is inherently one-shot because of the underlying quantum principles. No cloning applies, even with classical chat.
That's a neat trick. How do they construct that?
The core idea uses hash functions that are collision-resistant even against quantum attackers. They use these to sample the unclonable quantum states. And a really key building block they introduce is the one-shot chameleon hash function.
Chameleon hash. That rings a bell. They let you find collisions if you have a secret trapdoor, right?
Yes, but these are one-shot chameleon hashes. The trapdoor itself is single-use. Even the person who created the trapdoor can only use it once to find a collision for a specific hash value.
A self-destructing trapdoor. Okay, that fits perfectly.
It does. And crucially, for delegation using these one-shot chameleon hashes, all the communication can remain classical. Alice, sender, can be classical. Only Bob, receiver-signer, might need the quantum capability to use the one-shot trapdoor.
So the quantum part is localized.
Right. And the paper clarifies that one-shot signatures, the general concept, are broader than just these chameleon hashes. One-shot chameleon hashes are one specific way to build them.
I see. A specific tool to achieve the general goal.
Exactly. And they really hammer home the difference again. Classical one-time signatures are about risk if you reuse. Quantum one-shot signatures are about physical prevention.
Got it.
They position these one-shot signatures as a really strong form of quantum no-cloning, even stronger, they argue, than prior concepts like public key, quantum money, or quantum lightning, which were already seen as pretty advanced.
Interesting. So how do they actually propose building these technically? You mentioned a classical oracle.
Yeah, this is a key technical contribution. They construct one-shot chameleon hashes, and thus signatures, relative to a classical oracle queryable in superposition.
Okay, what does that mean in simpler terms?
It means the security proof relies on an idealized classical function, the oracle, that a quantum computer can query in a special quantum way superposition. This is considered a step up from needing a fully quantum oracle, which is a much stronger, harder to instantiate assumption.
So it's still a theoretical model, but maybe closer to something buildable.
Kind of, yeah. The construction itself uses clever ideas involving hash functions with periodic structures and ways to recursively divide up the preimages. It's quite technical. They do note a bug was found later in their security proof related to collision resistance against this specific oracle type.
Oh.
But they state it doesn't seem to affect the validity of the applications built using the one-shot signature concept itself. So a flaw in the proof of one specific construction may be, but not necessarily in the overall idea or its uses.
Okay, important distinction.
Yeah.
So beyond delegation, what other applications did the paper explore? You mentioned budget signatures.
Right, budget signatures. Think of a public key that comes with an initial budget, say 10 units. Every time you issue a signature derived from this key, you have to specify how much budget that signature consumes, say 1 unit. The signature is only valid if the consumed budget doesn't exceed the remaining budget associated with the key it came from.
So you can strictly limit the number of uses or maybe the total value signed for.
Exactly. They show how to build this using a tree structure of delegated one-shot signatures. Each delegation carries a portion of the budget down the tree.
Cool. What could that be used for?
Well, one direct application is quantum money with classical communication. The one-shot signing key acts as the quantum money state.
The unclonable object.
Right, and they use the delegation mechanism, which only needs classical communication, to transfer ownership. Combine that with budget signatures.
And you could potentially make the quantum money divisible, like transfer 0.1 units of your quantum coin.
That's the idea. Infinitely divisible quantum money using only classical communication. That's a pretty big deal if it pans out, as many quantum money schemes struggle with divisibility or need quantum channels.
Wow. Okay, what else?
They talk about decentralized, blockchainless cryptocurrency.
Blockchainless. How do you stop double spending?
By using one-shot signatures in a quantum lightning type framework. The inherent no-cloning, one-use property of the signature is the double spend prevention. You don't need a global ledger to track balances. The inability to reuse the payment signature prevents spending the same money twice.
So the crypto itself prevents the double spend.
Exactly. And again, they achieve this with only classical communication, which is an improvement over some earlier quantum lightning ideas. They even suggest it could be seen as realizing reusable proof of work without special hardware assumptions.
Mind blown. Okay, keep going.
Then there are ordered signatures. These ensure messages can only be signed in a specific order, like according to an increasing counter or timestamp.
Oh.
using the signature chain idea. Signature N can only be created if you have valid signature N1, and it includes a tag, like N, that must be greater than the previous tag. You can't go back and sign message N2 after you've signed N.
Useful for things where order matters, like, well, blockchains or logs.
Definitely. And building on that, they introduce single signer signatures.
Meaning?
Meaning, even if the secret key material somehow gets copied or transferred, the protocol ensures only one designated party can actually produce a valid signature at any given time. They show how to adapt ordered signatures using a counter to achieve this. Very strong control.
Yeah, that sounds incredibly useful for security.
Then delay signatures, take ordered signatures, and add proofs of sequential work between steps.
So you force a time delay between signing message N and message N+1.
Exactly. Requires real computation, real time to pass. One application they suggest is rate limiting the minting of new currency in a quantum money scheme.
Controlling inflation via computational delay. Clever.
And finally, they show one-shot signatures can be used for simple proofs of quantumness, proving you have quantum capabilities, and connect it to proofs of min-entropy, which is about proving the randomness of secrets.
So it's not just about signing things securely, it's a building block for proving things about quantum states and randomness, too. What a versatile primitive.
It really seems to be. The paper definitely paints a picture of it being a fundamental new tool.
Okay, those deeper technical sections.
Yeah.
Equivocal hashes, chameleon hashes. Can you give us the gist of the definitions and constructions without melting our brains?
I'll try. So, equivocal hash functions, they hash input to output, but also generate a quantum secret key. Given that quantum key and a target output, the public key, you can efficiently find pre-images, inputs that hash to that output and satisfy some extra condition, like having a specific bit value.
To find a special pre-image trick.
Right. And the quantumness of the key is supposedly essential to stop everyone finding collisions easily, preserving collision resistance. Their construction uses classical oracles queried in superposition, affine partitions, orthogonal complements, some heavy linear algebra over finite fields, essentially.
Okay, math happens.
The collision resistance proof uses quantum adversary methods. The equivocality finding the special pre-image uses quantum search, like Grover's algorithm on the oracle.
Got it. Quantum search finds the needle in the haystack, and the one-shot chameleon hashes.
Formal definition, hash function, where the trapdoor lets you find collisions for a chosen hash value, but that trapdoor can only be successfully used once for that purpose, even by you. They then prove this is equivalent to having an equivocal collision-resistant hash function.
The two ideas are locked together.
Yeah. They also mentioned building k-shot versions, trapdoor works k times, from the one-shot version, maybe by parallel repetition. And they stress uniformity, meaning you can't tell if a signature using the chameleon property was made by the original owner or the delegatee. Important for delegation security.
Right, you don't want the delegated signature looking different. And the budget signature construction, how did that work again?
Merkle tree-like structure. Root has the total budget. To spend delegate some budget, you create a child node linked by a one-shot signature, assigning it a portion of the budget. That node can then further delegate its budget.
So you have a tree of one-shot signatures, each carrying a budget commitment.
Exactly. Verification involves checking the chain of one-shot signatures back to the root and ensuring the budgets were allocated correctly and not overspent at any step.
It really does sound like one-shot signatures are this foundational piece you can build all sorts of amazing structures on top of.
That's definitely the feeling you get from the research. It's presented as a potentially core primitive for future quantum or hybrid crypto systems.
Okay, let's try and pull this all together then. We started with this idea from Justin Drake's talk.
Right, this overlooked concept.
Of a signature key that self-destructs after one use, enabled by quantum mechanics, destructive measurement, and no cloning.
The quantum poof.
And we saw how, through signature chains, this could lead to things like perfect finality in blockchains, dropping the threshold to 50%, instant validator entry exit.
Solving weak subjectivity, getting rid of equivocation, slashing risk, making liquid staking safer.
Yeah, really addressing some major pain points and limitations in current blockchain designs.
Definitely.
But then the research paper took us even deeper, showing this equivalence to equivocal hash functions.
And introducing one-shot chameleon hashes.
And using these ideas to build budget signatures, classical communication, quantum money, blockchainless crypto, ordered signatures, delay signatures.
Proofs of quantumness. It's a huge list of potential applications. many of which seemed really hard or impossible classically.
It really makes you rethink what's possible. And it circles back to that initial curiosity about quantum computing and blockchain security. It's not just a threat, right?
No, it seems quantum mechanics might also offer completely new solutions and capabilities we didn't have before. This could be a prime example.
From a simple key disappears idea to all these powerful applications, it's quite a journey.
It really is. It shows how sometimes a fundamental shift in the underlying physics, from classical to quantum, can open up entirely new avenues in cryptography.
It's complex stuff, no doubt.
Yeah.
And we've only scratched the surface here. If this sparked your interest, definitely check out the links to the talk and the paper in the show notes.
Absolutely. There's a lot more detail and nuance in the sources themselves.
But it leaves you with a pretty big thought, doesn't it?
Oh, yeah.
Well, considering these one-shot signatures are tied so directly to fundamental quantum laws, if they do become practical and widespread, especially as quantum computers get better, how does that change our whole notion of digital trust, of security itself?
That is a very big question. If the very nature of signing becomes inherently limited by physics in this way, yeah, it could reshape how we think about digital identity, authority, ownership, everything, really. Definitely something to chew on.
It's absolutely something to think about. We'd love to hear what you think. Any questions this raised for you? Maybe it'll lead us down another rabbit hole in a future deep dive, more quantum crypto maybe, or where blockchain goes next.
Always more to explore.
For sure. Thanks for joining us on this exploration into the kind of mind-bending world of one-shot signatures.